Hello, everybody, and welcome to the Future Leaders in Robotics and AI Celebrating Diversity and Innovation Seminar Series, sponsored by Microsoft DC Metro Engineering Site. All of our talks from this semester and previous semesters are available at robotics.umd.edu/futureleaders. This is a joint effort of the Maryland Robotics Center and Microsoft DC Metro Engineering Site. So today I am excited to announce our first speaker of the day, which is Dr. Catie Cuan. She is a researcher, entrepreneur, and artist, and she is a pioneer in the choreorobotics at the intersection of artificial intelligence, human-robot interaction, and art. She is also a postdoc in computer science at Standford University and recently defended her PhD in robotics and AI at Standford University's mechanical engineering department. During her PhD, she led the first multi-robot machine learning project at Everyday Robotics, which is also kind of known as Google X, and Robotics at Google, now a part of Google DeepMind. She has held artistic residences at the Smithsonian, the Exploratorium, Jacobs Pillow Dance Festival, Everyday Robotics, which is also Google X, TED, and ThoughtWorks Arts. So without further ado, please help me welcome Dr. Catie Cuan, and feel free to share your slides and get going.
Awesome. And here I will learn how to do this. Is my PowerPoint, which previously was available for me to share sound and optimize for video clip, and now no longer wants to be available.
Just a second, we need to promote you again.
Okay, great. Yep, okay, perfect. Now I can share sound and optimize for video clip. Awesome. And perfect. So can I get a quick thumbs up that everyone can see my screen? Amazing. Okay, thank you so much, Michael and Yancy, especially for organizing this great series. And I'm excited to be here with all of you. Happy Friday. It's hard to believe that it's already April 26th, but here we are. Today, I'm going to give you a fast and furious tour of what is choreorobotics, why it's important. I also just came back from the big TED conference in Vancouver, where I got to talk about exactly this topic. So a lot of these ideas, continue to be expanding and being adopted by various folks in the field. So I'm super excited to talk to you all about this today. So choreorobotics is teaching robots how to dance. And Michael gave me a great intro, and I will speak a little bit quickly about my background because I think it's germane to the talk, and then I'll go into some kind of high-level macro things that dance and robotics have in common, and then I'll talk specifically about a project that highlights this. So really quickly about me, this is truly my vision for the future of robots. We should be able to have robots that move around us, where we can have interactions with them that are seamless, fun, interesting, playful, and where we can be surrounded by robots and it feels natural and safe and kind of calm, and it doesn't have this strange factor that so many people have when it comes to thinking about robots in our everyday lives. And the way that I came into this space was I actually did my undergrad at UC Berkeley. I grew up in the Bay Area. And after I did my undergrad at Berkeley, I moved to New York City, and among other things, I was a professional dancer. So I danced at the Metropolitan Opera Ballet and a couple of other places. But I had this technical skill set. So I was also the vice president of a creative agency and did some entrepreneurial things. And so I had this kind of bifurcated career between my tech and my dance life. And then in 2017, I became the artist in residence at the Robotics Automation and Dance Lab, which was then headed by Dr. Amy LeViers at the University of Illinois, Urbana-Champaign. So I started dancing with robots mostly in my artistic work. And we then began publishing a series of papers about how people's perceptions of robots were changing when they saw them inside of a live performance and when they saw them inside of an artistic installation. And we wound up publishing a number of papers on this topic. We were basically treating a performance like it was a scientific treatment. So the same way that you might come in and have run an experiment with a robot, we were treating the performance just like that. This experience was so evocative for me, I decided to apply to grad school. So I did my master's, PhD, and postdoc at Stanford. And during my PhD, I spent 3 years at Google X, just like Michael mentioned, and I'll talk a little bit about that work today. I have performed and choreographed with more different types of robots than I think anyone on Earth. So I've used probably, anywhere between 14 to 15 different kinds of robots in my dance and research work. And I think this is important because they all move and dance in very different ways. And Choreorobotics is not kind of robot platform specific, but is much more kind of platform agnostic. What can we gather and learn from building these kinds of works? What do robotics and dance have in common? I think, Professor Barbara Tversky captures it fairly quickly here. She says humans have been moving and feeling much longer than they've been thinking, talking, and writing. The thinking here is a kind of TBD, but I think her point is really true, which is that we have sensation and movement, and they're a core part of the human experience, much more than speaking and writing have been. We've been just doing this as a species, for much longer. And movement is this core evolutionary quality of who we are, how we translate thought into action, and how we perceive the world. Likely nobody taught these kids how to play, but they somehow know how to navigate and play and run around each other and sprint towards the ball. And their bodies are being able to organize themselves through space to be able to go capture this ball that they're playing with. And it might even be that the purpose of our brains is to move around our environment in a meaningful way. So Bruce Hood is a neuroscientist at the University of Bristol, finds that 80% of the neurons are actually at the back of your brain in the cerebellum, the part of your brain that controls your movement. So it might even be that the reason we have a brain at all is not for these higher order thought processes that we always think about with brains, but it's just to be able to move and organize our bodies. And then one example of this is a sea squirt who swims all around the ocean, and then when it plants itself on a rock for the rest of its life, it eats its own brain because it no longer has to move. So there's such an importance around what movement does for even the way that we organize our brains and our bodies, of course. And then movement is deeply impactful to us as people. So these are a variety of different kinds of studies where they demonstrate that even these completely random, impoverished forms of movement have strong impacts on humans. So for example, here's a study on the far left where they show random collections of moving dots that are wiggling around a screen, where they have shapes that are being displaced in small ways in this middle study. And then finally, where they have an impoverished representation of a human torso in the far right study. And they find that even with these strange, kind of seemingly random representations of movement, people are saying things like, that makes me feel sad, or all those dots are going to the left, or they all remind me of this time that I smelled a flower in a park. And so you're associating semantics, memory, and directionality with these movements that are completely random. And so it shows that movement is so important in how we perceive and understand the world around us. And of course, what's moving now is robots. Robots are moving autonomously. This is kind of the first time that we've had things that are moving around in our environment that are not a part of nature. So they're not squirrels, they're not wind. Autonomous vehicles obviously kind of fall into this robot category. And certainly we've seen humans drive cars, but they're operated by another human being. So this is kind of the first time that we're seeing something move around in our environment that's not a part of nature. And its movement is so primary for us. It's maybe potentially the first thing we notice about the robot is how it moves. And then we have a number of examples of where these robots are showing up, everywhere from grocery stores to hospitals. And so this problem about how can we have robots move in ways that are legible and understandable to people is super important at the moment. And who studies movement and thinks a lot about movement are dancers and choreographers. And this is where this intersection of choreorobotics emerges. So movement winds up being this primary way that we perceive and interact with robots. In an early version of KiwiBot, people were not going up and speaking to it. It wasn't about language. It was really about pure motion. So what do choreographers and roboticists have in common? Variety of things. So choreographers need to be able to describe and translate movement through scores, teaching, and recording. So if you were a dancer, let's say in 1965, and you wanted to be able to learn a dance that had existed in 1950, you would look at choreographers who had created their own lexicons and their own written vocabularies for what these dances could look like. And these are some examples from Merce Cunningham and Lucinda Childs. And so dancers were passing these dances through each other and translating these movements through various kinds of scores, teaching, and recording. Of course, this changed quite a bit when video came around, but even still, you're having to demonstrate a dance through various kinds of written transcription because it helps capture details that you might not get otherwise. And roboticists do something very similar, right? They try to translate movement through recordings, demonstrations, equations, and more. Roboticists and choreographers also might use something like state machines to allow room for uncertainty. If you want to create a performance where you're not scripting every single beat all the way through, you want to create opportunities for choice making. This was a performance at Princeton where Rebecca Legier did exactly this. And then, of course, we all know, for all of us who have programmed robots, that it's really hard to be deterministic about everything. So we need to have state machines where robots can make choices within that environment in order to allow room for uncertainty and choice making. And then, of course, choreographers and roboticists also rely upon cues and patterns to convey legibility and intent. So in this, on the left, this is the Firebird from American Ballet Theater. Alexei Ratmansky's the choreographer, and he's got Misty Copeland in the middle. And without ever having seen this dance, you can draw a lot of conclusions about what's happening in this image. You could say, look, she's red, she's elevated, she's in the middle, all these people are circling around her. And so there's such an obvious, she's so clearly important. And so never having seen this dance, you would use these existing cues and patterns to understand what's happening in the image. Obviously, there's some canonical work from Anka Dragan during her PhD that looked at functional movement is actually not the same as legible movement. So having a robot that can move in a functional way is not necessarily what's going to be the most legible to people, or even potentially predictable for people. And so choreographers and roboticists need to understand these kinds of existing priors that people have when they're conveying legibility and intent. And then finally, choreographers and roboticists need to make motion. It's got to come from somewhere. And choreographers might come from a particular artistic angle or a desire of something they want to convey inside of a performance. These are a couple of examples of cases where actors and choreographers have collaborated with roboticists in order to create new motions. On the left, they basically were trying to animate this seat cushion that you could put your feet up on, this ottoman. So they worked with actors to be able to do that. And then on the right, this is some work from my former collaborator, Amy Leviers and Umer, where they were looking at, we don't care about having the most efficient walk, but we care about having the most number of choices that we can possibly have, all the different kinds of gaits that we could create. And this is what allows you to have a big design palette of different kinds of motions to choose from. And then finally, I would be remiss if I did not mention that there is a long history of people making dances with robots, basically since the late 80s, early 90s. I think one of the first robot ballets came out of Stanford was Margot Apostolos in 1989. And so people have been making work in this domain for quite some time, everyone from Daniela Roos and Palabolas at MIT CSAIL up to William Forsythe. And then a few people who are kind of more contemporary. This is the Choreorobotics 101 class that's taught at Brown right now University, and then also some recent work from Kate Sicchio, Amelia Virtue, and Kim Baraka, and sort of various new faculty that are coming up in this domain. So now I'll turn to a project that I worked on during my PhD and kind of afterwards while I was an artist in residence, and then a software engineering manager at Google X. And so this is two projects that are interlinked called Music Mode and Interactive Robot Flocking. And we will sprint through these because that was a nice long intro into what Choreorobotics is. But here I'll talk a little bit about why we built both of these projects. So we had all these robots. We had 180 robots that were running around all these different buildings at Google. And they were kind of boring. They were not that exciting to be around. And so we had this motivation, which was, how could we communicate information about the robot's state while also increasing likability, comfort, and trust amongst all these different human bystanders? So these were robots that were wiping tables, sorting trash, doing very functional things. They were not particularly welcomed by these various Google employees inside of this office. And so we started looking at some other spaces, autonomous vehicles, where people were sonifying the vehicle to make it clear what the vehicle was trying to do. And then also looking at other instances where you could use sound and kind of haptics cues to let people know what the robot was up to, because we weren't going to modify the hardware of the robot at all, but we were going to modify everything inside of software. So I had this idea, which was, why don't we teach the robots how to play musical instruments? So they'll wipe tables for a little while, then they'll go over and they could play the cello, and then they'll keep wiping the tables, and people will be so enamored by the robots. And one of my colleagues, Tom, said, instead of getting the robot to play the musical instrument, what if the robot was the musical instrument? And we could take all of these different sensor streams that we have on the robot, pull them off and sonify them and turn them into music. And so this became music mode. So what we did with music mode is we took every joint on the robot and we turned it into we mapped it onto a sound. So hopefully y'all can hear this. But for example, every time the robot would move its shoulder, this was the sound that people would hear. So for all the musicians out there, you know that we had so many different combinations of all these different sounds, right? So we had 8 joints and they could be played in any combination at any time. So you could have a gripper while the head's moving, or you could have a shoulder, an elbow, a wrist, a gripper while the bass is moving. And it wouldn't make sense for us to do these on a scale like da 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 da, because you would hear all these weird chords that didn't make any sense. So this is why we wound up artistically and musically having each of these joints be mapped to a different instrument, and then having some of those have melodies, and then having some of them have tempo. So this was kind of a big puzzle for us to put together from a music standpoint, and we needed the artistry to make just as much sense as the engineering. So the sound selection took quite a bit of time. First, we implemented this on a laptop. So we would pull all of these sensors or all of the signal streams off of the robot. We would do a little post-processing, clean the signal up, turn it into a MIDI message, pipe it through a digital audio workstation, and then stream the sound out. This worked okay on an external laptop, but we wanted to be able to do it locally on the robot and play it through the robot speaker. So we wound up doing this instead, which was basically the exact same thing, but bypassing the MIDI message and the DAW and having it just trigger a sample that was locally on the robot and having it play the sound. So this is what it looks like on the robot. And this is what it looks like when many joints are moving at once. This feature became so popular that we put this on all 200 robots, and we could turn it on or off at any time. So people could turn it on while the robots were wiping tables. And so you would have these robots that were kind of navigating around the buildings, and then they would start wiping tables, and you would hear the symphony of what that sounded like. And I started to get a bunch of cold emails from various engineers who were like crying in the middle of the day because they saw this robot like playing beautiful music. And we wound up making a couple different versions of this music mode. We made one where each joint was a string and a guitar chord. We made one with a bunch of house music, so kind of like layer on top would be kind of fun. And this feature, I mean, really just exploded and started to get adopted by all these different people so that they could watch robots play music anytime they wanted. We then ran an experiment on it. So we had these 3 different sound conditions, the kind of silent, which was without sonifying the robot's motion. We did one with robotic sounds and then also orchestral. We had the robots perform 3 different kinds of tasks. So navigating, wiping tables, and doing a sort of dance motion that I just showed for all of you. And what we found was pretty striking. So basically, while the robots are playing music mode, they're found to be more anthropomorphic, animate, likable considered to be smart and considered to be safe. And all of these were highly significant with an N of 18. We then also found that it didn't have a big effect on task success, but it did for people. It made it more clear what the robot was going to do. And they also said that they would be more comfortable around the robot if it was indeed playing this music mode condition. We also ran a case study on this. This paper is currently in review. And then we ran a second experiment where we were like, well, is it that the music is actually tied to the movement, or is it just that the music is nice? And so we ran an experiment where we had the true music mode version that we had written, where every time you moved a joint around, it was triggering our sample. And then we had a random condition where just nice music would play near the robot at all times. And what we found here was that actually linking the robot's motion to the music means that people like the sounds more. And also that they, I don't know why this one didn't highlight, but also that it was found to be linked with the robots more intelligent. Oh yeah, there it is on the right-hand side. So it was considered to be smarter and they liked the sounds more if the sounds were actually linked to the motion. So we find that it's not sufficient for robots to be playing nice music, but it's if that music is indeed tied in some way to what the robot is doing, which goes back to our original hypothesis. So with music mode, what we did was we created this technique to generate music based on robot movement. We ran these experiments in a case study to verify that these changes did kind of give us the intended result of improving the perception of the robot. And so finally, now that we could get the robots to play music, we wanted to get a bunch of them to move around. And this is why we created this interactive robot flocking project. So really the goal here was we foregrounded very much the technical contribution as much as the artistry. And so how could we create a sort of compelling, rich experience with multiple robots that would create positive emotional responses and that people could interact with and kind of move around with a lot of robots at the same time. And we found, there's been obviously quite a bit of work when it comes to humans doing single human multi-robot interaction, which had kind of directive impulses or, getting robots to be organized and do things together. But we were very much more interested in, can we kind of evoke people emotionally and can we get them excited about wanting to move around with a bunch of robots? So here's how we designed the whole thing. We had this parent client, which was talking to all of the robots simultaneously. So, Robot 0 has this client flocking service that's connected to all of these various sub-services, which are controlling different parts of its behavior. So we had something that changed the arm, the base, the overall choreography, and the human tracking that was talking to the parent client. And then we would hook all these robots up to the parent client. So we had perfect information about where all the robots were at any given time and to make sure that they were all tracking the same humans. Once we had this system design, we had various algorithms to control the base. So this was our kind of flocking default behavior, just on an XY plane, weight modes, which I'll talk about in a second, and then how we respond to gestures from humans. For the arm, we had a choreographed arm motion that we would interpolate between at random. We also allowed people to contact the robots during this experience. So we needed to do force detection, and then the gripper would respond to various gestures that it saw from people. For our head, we had a default controller of how the head was controlled. Super important because we have a bunch of cameras in the head, and that's going to dictate where the robots should navigate next and where the human is that they're perceiving. And then, of course, in the light ring, this was also responding to whether or not it saw humans and whether or not the humans were doing gestures. And then at the same time, all these joints were playing music mode. So this took us, we basically wrote code, I think, for 18 months to get this entire system to work. We tried to do it as like an end-to-end reinforcement learning problem at first. That did not happen. So we switched over to this new strategy, which I'll show in more detail. But these were all the components that were running for each individual robot as they were all streaming this data up to the parent client. So we started with a canonical flocking algorithm called Boyd's algorithm, which I'm sure a lot of folks are familiar with, which has three, they don't tell you exactly, well, it doesn't say in Boyd's algorithm how to implement all these things, but it's very, very high level. So it says cohesion, robots stay together, separation, robots stay apart, and alignment, robots, align their velocities, the speed and direction in the same place. And in Boyd's algorithm, you then have all of these different gains that are associated with these various three functions, and you can oscillate those gains to get different kinds of flocking behavior. So what we did was we added a bunch of terms onto Boyd's algorithm. So we had a circular goal. This was getting robots to move in a circle, follow the human, which was if there's a human in the scene, follow the closest one, move along this linear line, and then avoid the bounds. So avoid the boundaries of the space. So then we mandate that our next robot X and our next robot Y is this cohesion gain times that cohesion function that I just described. We do this across all 7 of these functions. So you've got various gains that are associated with each of these functions. You add them all up, and that's what gives you your next X and your next Y. And then our weight mode is that we can learn all these gains, and that will create different kinds of behavior. So we can learn these gains, in our case, using a very simple linear regression, where we're able to create different kinds of behavior that are evocative and get different types of flocking based on different organizations of these gains. So we have these 7-dimensional vectors that are comprised of each of these gains all stacked on top of each other. And then we can select between those different sets of gains, and that's what gives us interesting flocking behaviors. So when we change all these gains, these are the kinds of behaviors we get. So we get something that's default, which is kind of a nice looking flocking. We're trying to capture X, Y, and time here. So that's how the color is changing. So it starts in this kind of light color and then it winds up in a dark color. So you can sort of see where the movement is going over time. We get this following behavior, something that looks like a firework, fishbowl, pacing, joining, coming together, things that are more parallel. So we can create all different kinds of beautiful flocking motions simply by changing these various gains. And then we train an agent to select between the gains in order to build the most interesting experience over time. So we have these hand-defined weight modes, which it describes are these selections of gains. We have our hand-tuned features, which are, what's the thing we chose last time? How are we organized right now? Where's the person relative to where we are? And we can obviously learn something that allows us to select between these gains to give the most interesting overall experience. So this is an example of what a couple of these behaviors look like. So we have something that's a fishbowl behavior. This is following. This GIF got a little discolored, but hopefully you can still see what's happening. They basically follow me around the space, all these different robots. Some people get freaked out by this. I definitely did not. Then we also have this kind of parallel behavior while they're also avoiding the bounds, and they're selecting this sort of distance between each other, based off these various gains that we've just demonstrated. Obviously the separation term is still involved in this one. And then, as if that wasn't enough, we added a bunch of gesture recognition on top. So if a person put their left hand up, the robots would open and close their grippers, which triggered that bell sound. If they put their right hand up, they'd rotate in place. And if they put their hands together, they'd look up at the sky. And this basically allowed you to play the orchestra of all these various robots by moving around gestures and then also where you were configured in space. And I've got 2 minutes, so I will tell you what we then did with this whole experience. Well, here's Millie, for example, putting her left hand in the air, and then the robots are opening and closing their grippers. And so you can hear the bell sound that gets triggered. And this is what everything looks like all together. All the robots playing music mode, all of them running this flocking algorithm on all the different components. So of course, because we're good scientists and engineers, we ran a big experiment on this as well. One of the things we captured, though, were qualitative comments, and we heard, "I feel like I'm in heaven. Am I ascending? They were so cute out there singing and dancing. I have no idea what they were actually meant to be doing, but it made me happy. This feels poetic. I'm having a visceral reaction. Little ducklings. I feel like I'm watching an alien species performing," and then reminded me of watching an aquarium of fish. So people were having very, very strong reactions to what they were seeing inside of this kind of installation and performance. And then we found, that we tested all these different weight modes, and we found that people really liked the one that had been selected by the human more than anything else. So if there was a person who was sitting behind the screen and kind of selecting between different weight modes, people tended to like that the best. So the robots paid attention to me. I enjoyed being around the robots, versus the agent and the algorithm that we had trained. So we still, it wasn't statistically significant. We still needed to kind of determine exactly how we could imbue all of the nice human preferences inside of this AI agent. But overall, people were just kind of so overwhelmed by the experience that the weight mode selection didn't have as much of an impact on them. And so I will wrap up here and say that we created this flocking algorithm for robots to move in groups while also responding to human gestures and playing music. And then we ran this experiment to verify these changes and how the perception unfolded. So for anyone who wants to keep in touch, who's got questions and comments, here's my info, and that's a wrap.
Yay. You have to make do with us clapping only. Presenter people, but a wonderful talk. Thank you very much, Dr. Cuan. So we have time for only a quick question or two, and I'm going to take advantage of that myself. So in the dance stuff that you do, and like going out on a limb, dancing often involves like lead and follow and some interaction there. And in the swarming stuff, it looked like you were kind of the leader and the swarm was kind of the follower. But I'm curious how much of the programming of the robots and how much of you as the dance person like are compensating for the other side of that equation. Like how much does the human and the robot need to compensate for the other one in the dance?
That's a good question. I think, and it's always, if people will say to dancers, it's good to learn how to perform. It's something even harder to learn how to improvise. And in a true improvisation, you are not especially leading or following 100% of the time. You are being impacted, you're being influenced by where the robots are being influenced by you. And so you're actually in some kind of true improvisational exchange, which is what happens in everyday life. If you see a robot that's trying to pass you on a hallway, you might take a step to your right as it takes a step to its left, and you're sort of trying to have this real-time improvisation. And I think that's why we had, everything inside of our flocking algorithm and our perception was all completely dynamic, because we wanted there to be a good amount of choice making on the part of the robots. For example, when I was playing around with the system and the robots would all move in one direction, I was like, oh, I want to go over there. And so I would go follow the robots where they were, as opposed to them having to follow me where I am. And so I would agree with you that I think the kind of leader following is something that does happen in dance, but to bump it up a level of sophistication is how can we create room for true improvisation where there is not a leader or a follower? And the answer is to be able to make choices quickly, to learn on the fly, and then respond to the environment as quickly as possible with your perception system.
Awesome, great, thank you very much. I have one more question. I think we have barely enough time for. And I liked the idea that, like the engineers were very moved by these robots playing music, like as they were running around and doing stuff. And I'm curious, like, as not an expert in this, like the music that you were playing was super nice sounding and sounded like it'd be fun, like the layering that you said for like the more funky music or the techno music. I'm curious if you looked at or would consider looking at like if you played like just non-music noise as the robot was moving, and if that would have the same or a different sort of reaction from the humans, or any thoughts about that?
We did have a condition in our first experiment, which we called robotic sounds, that all that was essentially an amplification of the robot's existing sounds that were played in this dynamic fashion. So if you moved your shoulder around, you heard an amplification of the existing motor sound of the robot's shoulder. And people just hated it. That's where we saw such strong significance in between the orchestral version and the robotic sounds, where essentially if a robot sounded like a robot, the motor's like, like people found that so off-putting and kind of a true white noise, like a loud refrigerator, basically, that you don't really want to be around. And so in that case, we found that, effect to be very strong. If the sets of sounds were different, I agree that would absolutely have an impact on how people perceive the robot. And the argument that we made in the paper was, look, there's an incredible amount of subjectivity in engineering in general. you know, how we choose to orient limbs, how we choose to, you know, even the proportions between the various joints, like all of these things, we think that they're, you know, completely, you know, unimpactful for humans, but they're all deeply subjective and they're all totally design based. And so we try to demonstrate that we've chosen selections of sounds that are diverse enough that we can really observe this effect, and at the same time recognize that we made choices in that process.
Awesome. Thank you very much. And thank you for joining us again.